Hi, Year 11s. So, like I mentioned in class the other day, I was just going to record this video about the last little bits of chapter 2.3. After we've done this, you can then attack pretty much the entirety of it, of the questions in the textbook for this subtopic, and we can then move on into topic 4. Topic 3. Okay, now the second last thing we're going to be doing is percentage composition. So we're looking at for any particular compound, we're going to investigate the percentage composition of that compound contributed by any particular element. So you'll see examples in a minute, but this equation just here is the one we're going to be using. Now, the percentage composition of a particular element within a compound is the molar mass of that particular element we're interested in. N is the number of atoms of that particular element within that same molecule. So again, we'll have a look at an example in a minute. But then you divide it by the overall molar mass of the compound that element is in, and then you multiply it by 100. So this one here is just the decimal. Once we multiply it by 100, we get our percentage. So as I've said here, M element is the molar mass of the element, straight from the periodic table. N element is however many of that element there are in the molecule or the compound, and then M compound is our overall molar mass that we've calculated. So our example is going to be nice and simple. It's going to be looking at water. Now, if we look at the hydrogen first, we use the molar mass of hydrogen straight from the periodic table, which is 1.008 grams per mole. Now, within water, we have 2 atoms of hydrogen, so we multiply that by 2, and then we calculate the molar mass of water, which will be 2 of hydrogen plus an oxygen, giving us 18.016 grams per mole. And then finally, timing it by 100. Now, I have a final value of 11.19%, and I have made sure to have the 4 significant figures because our molar mass has 4 for both of our values that are being divided. Now, this one here, this value, this 2, it only has 1 significant figure, but it is an integer. It's just a multiple, so that doesn't count. These significant figures only count for things that that have been measured to some sort of accuracy. If we're just multiplying by 2, a whole number, then that doesn't count. Now, so we have 11.19%, and that is from the hydrogens. Now, you can find out the composition of the oxygen in 2 ways. Either you can repeat the calculation that we just did, but instead of for hydrogen, do it for oxygen. You can also know that because water is just hydrogen and oxygen, if 11.19% is hydrogen, the rest up to 100% must be oxygen. So if we do it that easy way, 100% minus 11.19 gives us a remainder of 88.81. So hopefully our calculation that we try instead also equals that. Now, if we look at oxygen percentage composition, we have the molar mass of that element, oxygen, which is 16.00 to 4 significant figures. I believe it would be 15.998 or something like that, which rounds up to this. We multiply by 1 because that's how many atoms of oxygen there are in water, and then we divide it by the molar mass of water again, as we had before. Multiply by 100 and you end up with 88.81%, which is what we calculated before. So now we've calculated the percentage composition of each of the elements that make up water. You can do the same thing for any particular element within any compound, no matter how large or small it is. So there will be some questions that you can try in the textbooks, and you'll be ready to attack the percentage composition ones. Now, there is the last little bit that we're going to be looking at, and that's something called deriving empirical formulas. Now, first of all, this is coming off the back of the percentage composition that we have calculated up here. an empirical formula, well, first of all, I need to go through that as well. So an empirical formula, you may or may not have heard of already, but it will be the smallest unit of a compound, where you are just looking at the ratios, or the smallest integer ratios of all of the atoms in it. So again, I drew a little table here to illustrate what I mean. So if we have a substance such as butane, so butane has a molecular formula of C4H10. So there's 4 carbons and 10 hydrogens. If that's the molecular formula, so that molecule has that many atoms. But the empirical formula instead is looking at the lowest, the lowest integer ratio of those atoms, and both these numbers, 4 and 10, can both be divisible by 2. So if we do that, we end up with C2H5. So that is showing us that for every 2 carbon atoms, there are 5 hydrogen atoms in butane, even if that's not the actual formula of the molecule. Similarly, for hydrogen peroxide, its formula is H2O2. Now, as you can see, there's 2 hydrogens and 2 oxygens, but both those values are 2. We can divide both those by 2 to give us our empirical formula of OH. That's showing us that for every hydrogen, there is an oxygen, and vice versa in hydrogen peroxide. So if we find percentage composition results from, let's say, an experiment, we can work out the empirical formula of a substance. So even if that doesn't give us the actual formula, it does tell us at least that the real molecular formula is going to be some multiple of those atoms. So if, for example, we calculated this C2H5, we know that our final substance will be some multiple of this, either C2H5 or C4H10 or C6H15, that sort of thing. Okay, now I'm going to just hide the first the calculations, so you can just see the bottom here. Now, if we're given, or we can be given these mass percentages similar to the ones we calculated before, but we find these out from, let's say, an experiment. The first step is to write out all those percentages along with those atoms. And then what we do is we divide each of those percentages by the molar mass of that particular element. So without showing you the calculation, carbon, we'll be dividing that by 12.01. Hydrogen will be 1.008. Nitrogen will be 14.00 probably. And oxygen will be that 16.00 that we saw before. And look at that, nitrogen is close. I just went to another significant figure. It's not really a big deal. Either way, so if we divide those by each of those by the molar masses of the element that is associated with that percentage composition, we get these numbers here. So you get 4.33, 4.33, 1.45, and 1.45. These numbers will be different for every substance that you're looking at, because the percentage compositions will be different. Regardless, we end up with those values there. Now, what you need to do is you need to find the lowest value out of those values, and you see that 1.45 is repeated, but it is also the lowest value. So we need to go through and divide each of these values by the lowest across the entire thing. So in this case, we're going to divide everything by 1.45. In this case, it's coincidental that both these values are the same as each other. It doesn't always have to be the case, often won't be. So if one of them is the lowest, you divide every other number by that number. So we'll do this. 4.34 divided by 1.45. Again, 4.34 divided by 1.45, and so on. Now, obviously, these ones, you should hopefully know the answer to that. And without using a calculator, it will be 1. So that's showing us that nitrogen and oxygen will have in the empirical formula, there will be 1 nitrogen and 1 oxygen and some multiple of carbon and hydrogen. And once you work it out, those two values are very close to 3. And obviously, these ones will be exactly 1. So in this particular calculation, it doesn't matter if these are 2.98 or something, or 2.97, or they could be 3.05 or whatever. If they're really close to a whole number, that will be the number you go with. If instead this number was like 3.3 or something, then that is too far away from 3, and we know we want to get them all to whole numbers. and we might need to multiply this by 3, for example. If we multiplied all of them by 3, then these 3.33s, if that was the case, would get them to a whole number. Okay, so having these values here, pretty much 3, exactly 1, gives us our empirical formula of carbon with 3, hydrogen with 3, nitrogen with 1, and oxygen with 1, which we see just here. Now, the molar mass of this empirical formula is close enough to 69 grams per mole. Now, what a question will also add is knowing, or once you've calculated the empirical formula, it will tell you what the actual molar mass, it may tell you what the actual molar mass of the real molecule is. So if the molar mass of this unit is 69, the real molar mass for the actual molecule will be some multiple of that, some whole number multiple. So it could be 1. So for example, this could actually just be the molecule. It could be twice that, 3 times that, some multiple. So if we look down here, if they've given us a value of that 207, we know that 207 is going to be some multiple of our 69. So you do 207 divided by 69, that will give you, so 207 divided by 69 will give us something like 3, or close enough to 3. And that's what that does work in this case, which means for our actual molecule, which was always going to be some multiple of this, our actual molecule is going to be C9H9N3O3. And that is it. So now that we've learned about this, you can, if you didn't understand any of these particular steps in the textbooks, whichever one you have, you will find this explanation again, just not in my words. You'll also find more examples, and you're also going to find some additional questions which you can now get done, which I would like you to get done. Awesome. Have fun. I hope this all made sense for you.